Hello, today we are going to solve another rectilinear in a rectilinear question in mechanics dynamics. We're going to solve this one here. To 8, a particle moves along a straight line with a velocity in millimeters per second given by this formula equation. You are supposed to calculate the net displacement and total distance d traveled during the first 6 seconds. Okay, we're going to use Creo mechanism to solve this. Let's now go to the Creo. I'm going to set my units to be millimeters per second here. Set them. See, okay. Now I'm using millimeters per second. You can see here, I'm using mm. This one is at Kelvin and seconds cross. Then we are saying what? We are saying that moves along a straight line. This one is a kinematic, it's not dynamic, because whenever you see a straight line motion, it means the effect of gravity are not considered. Therefore, I'm going to create a particle that will move on a straight line. Therefore, let me just say my particle here, just to present the motion. Let me use default, and let me activate a sketch something that is moving along the horizontal plane. Let me just revolve something there. I'm assuming, or just let me make it more fun. Let me just extrude here. Maybe it's a car. Yeah, just to make it more fun here. Oops. I'm supposed now to trim. Yeah, that's my particle. I don't need to fully define my sketch, just for presentation. Let me use symmetry like that. That's my particle that will be moving on a straight line. I'm going to use this as a car. Forgive me. Therefore, if I go back now on to make this to move on a straight line, therefore what I need to do is I need an axis that represent the motion direction. Let me create an axis between those two planes there. Let me put the axis there on top. Therefore, if I go back here, I can now delete my default. This can move, you can see they can move, and I want to maybe use slider. I want to slide maybe this edge along this like that. Then to avoid rotation, I can say this plane and this plane to be parallel or distance constraint there like that. Therefore, if I view from this side here, now my particle can move on a straight line like that. Therefore, let me just hide these ones here. This one here is our right plane for the particle, and this one here is a right plane for the assembly. We are going to say that initially these two are coincident. This is our starting point. Therefore, I need to define this being I want to define this as my initial or starting point. If I go to drag here, I can say constraint. I can align this plane to this plane here using the first one here. Align two entities, this plane to this plane. Take a screenshot and say my zero position here. 0 position. like that. Then you can cross. Therefore, in case you move it, for you to go back how it was, just go here and double click. It goes back to the 0 position. And you know that for the kinematics, you don't need to define the gravity, the mass. We don't need those. This one is a rectilinear motion. If you go now to the application mechanism, we need not to define. If I go back here, this is the connection. This is joint. This is the joint we have defined. That is a translation joint. Let me just go back and rename the joint here. Instead of having a name connection 1, I can say this one is a let me just use the name here, straight line motion. Straight line, yeah, can give it straight line motion. That's the axis, the joint axis that represent the straight line motion. That, let me see if it was able to, yeah, straight line motion, yeah, that is what I want. Therefore, if you go back now to mechanism, if you move it a little bit, just move it a little bit like that. If you go to connections here, you should see a straight line motion. And I want to define also, I want to define the 0 position of the straight line motion here. If you right click here, select edit definition, you select these two planes. You can see the distance is negative 1 1. I want them to be at 0, those two. Then set that to be 0 position, then enable regen value. If you press Ctrl G to regenerate, it will always go back there. Therefore, if I move it like that, if I press Ctrl G, it goes back to the initial position of the joint here, connection. Then now we need now to define the motion of this joint. Yeah, the motion of this joint is facing this direction. No wonder why it was saying it has a negative. Okay, that's fine. Let's go to Control G to regen. Now I need to define 400 minus 16t squared velocity. I need to select servo motor, and as a velocity driven entity, it is this joint. Ball is on this direction. You can flip direction here. I'm using a servo motor with a velocity, and here we have to define the actual joint, straight line motion here, you can see. Then the motion type is user defined. This one is a user defined. Now, being a user defined, you have to use an expression here. You add expression segment to the table here. Then you select edit. We need now to type this equation, 400 minus 16t squared. You can say v, just write equation there, 400 minus 16 multiplied by t to power, what is power? Yeah, this one here, to power 2, like that. You can say okay, 400 minus 16t squared. This one is my velocity equation in millimeters per second, and it is acting onto this joint axis. Then say okay. We have defined our motor. Let's go here. You can go to motors to see your servo motor. It is edit. We can give it a name, properties here. Let's look for a name. You can say v profile, like that, and you can graph this v profile to see how it will look like from 0 to 10. Let's see. This will be velocity. Let's see if this makes sense. 400 minus 16t squared. at t0 it is 400 here. When t is 1, when t is 1, we should get 400 minus 16, that is 384. When t is 1, we should get around 384. Yes, you can see we are getting 384. You can see 1 versus 384. Therefore, the equation, the profile is okay. That's how you can do a quick validation of your profile. Therefore, you see okay. Next is you need now to define the initial condition here. And we say the initial condition is supposed to be 0 position. It will always start at 0 position. Say okay. Just hide these planes. Then we need now to go to, we don't need gravity. We just do the mechanism analysis. The type is kinematic because we don't have the effect of the gravity. If you have the effect of gravity, you have to use dynamic because we need to enable friction, all this. But now it's just a kinematic. There's no external load, there's no load. If you want to study the motion of object without considering the loads, you do the kinematic. Therefore, and we go back here for the first 6 seconds. Therefore, we just need to define eddy time to be 6. You can use 0.1, that's fine. And initial position my 0, initial configuration, start from a 0 position, then say okay, like that. Then lastly, you need to define what are you calculating. Calculate the net displacement and total distance d. Okay, therefore we go to the measure. We are measuring what? Position. We are measuring position here. We can say motion profile or full motion. Let's use the word full motion of position of this axis. I want to say at time equals at each time interval. Can do like that. I can create another one. You can say dist at t6 as well, position of this at time equals 6 seconds, like that. Apply, say okay, close. Therefore, if you now analyze this, you go now to the mechanism, analyze mechanism, run to moves from here to there. Let me just go to the front. Therefore, you need to know the distance there. If you go to measures here, you can see we are getting 1248. We are getting 1248 here, 1248. Then you close. Then because we saw that the velocity, this will go back a little bit because now this velocity is when this is 6, when this one is 6 squared, the velocity becomes negative. Therefore it starts to go back. For you to get now the precise displacement, that's the total distance, that's the total displacement. For you to get now the actual distance, you do what we call trace curve. You trace a point, and let's trace this point like that, and you preview, or for this results you preview, then say okay. You'll see that this is the start point, but you can see this axis here, this sketch, this one is sketch, goes all the way to here. Therefore, what we do, let me just change the wireframe because I want to see. In fact, let me hide this part. Let me hide it for ease of visualization. Therefore, from this point, this is the total distance that was traveled to this point. Therefore, if you just go and measure this here, let me just cross here. We saw that this one is 1248. Okay, let me cross here, save. If you now measure this here, analysis, measure distance of this, we'll get another. You can now measure, let me measure from this one here. Okay, for some reason, let me see, measure that. We are getting 1418. The 1418 is the total distance from here to here. The one we found 12 something, that is the displacement. That is how you can perform this type of analysis. Yeah, let's check the answers to see if we got it right. Yeah, we can see we got total distance as 1419, but displacement is 1.2 because the car moved from point A, went to this point here, then went back a little bit because we got a negative velocity. Therefore, the final point was here. For you to get displacement, displacement is from this point, it's from here to here. This one is a displacement. We just see the actual, it was here, the initial point was here, final point is here, but the actual total distance is from here to here. You see? Yeah. Therefore, yeah, that's how you conduct the dynamic analysis in Creo. Thank you, and stay tuned for more.